Alright, now we have expressions, we have minus beta UW and plus beta UW. They are the two gradients on the right hand side and the left hand side. So we can now calculate the difference, because that's what this whole technique's all about, and you'll see why later, but for the moment just patience, right? Okay, so now we find the difference between the gradients, just as we did here. So the gradient on the right hand side minus the gradient on the left hand side, same here. But this time we're calculating this difference in the gradients by using the wave function, the u, in regions 1 and 2. Right? And it should be this difference in the gradients. Since this gradient and this gradient are the same, and this gradient and this gradient are the same, given that, therefore, just logically follows, therefore the difference between that one and that one should be the same as the difference between this one and this one. Makes sense? Yeah, I hope that's obvious to you, right? Well, we've already calculated the difference between this and this, and that should equal the difference between this and this. Now, what is the difference between this gradient and this gradient? Well, it's the gradient right-hand side, which is here. So it's minus beta UW. So minus beta UW, and then minus the gradient on the left-hand side, which is plus beta UW. But you're minusing it, subtracting it. So you get minus beta UW minus beta UW. That gives you minus 2 beta UW. Right? Now, what I just said before, the difference in the gradients in the 1,3 region should be equal to the difference in the gradients in the 2 region. So this gradient difference and this gradient difference should be the same by continuity. Right? So therefore, here's the difference in gradients using the u in region 2, and here is the difference in the gradients using the u wave function in regions 1 and 3. Right? Now those two differences should be the same, equal. So therefore, this minus 2 beta UW should equal this expression, minus 4m delta h over h bar squared UW. Okay, so this and these two should be equal to each other. Right? So therefore 4m delta over h bar squared should equal 2 beta. That's what I've written here. Okay? Okay, cancel out the 2's, so you'll get 2m delta over h bar squared equals beta. Now, what is beta? Well, I've done that before, so it's just the square root of this term. So square root of 2m into v0 minus e over h bar squared. Okay, so square both sides, get rid of the square root. So you get 4m squared delta squared over h bar to the 4th, and here 2m v0 minus e over h bar squared. Cancel the h bar squareds, cancel the 2, cancel an m, and you're left with v0 minus e, that's here, equals 2m over h bar squared. Aha! Ding ding, ring a bell. We saw this in the previous session. This was your expression for E. See, you know the size of your well. It may be very large, but given the size V0, the depth of the potential well. So you know V. Now it's a well. It's a delta well. So your delta here will be constant, and you know what that is. If you know the width, if you know the A and you know the V0, you can calculate delta easily, just the product, just A times V0. So you know delta, you know your Planck's constant. So you can calculate the E. You just take the E across, bring this over. So you've got a formula now for the energy. So in other words, in other words, using this difference in the gradients technique, we were able to find the same expression as in the previous session, which was fairly tedious, a lot of algebra. But nevertheless, we still needed the analysis of the previous session because, to get this. And we needed that in this session. Okay? Right, so we now have a second technique to find the eigenvalue, the allowed energy. And there's only one for one spike, one delta well, right? And here's the expression for it. But this second technique is so much easier and handy and convenient to use when you have multiple delta wells. So, and from that, the techniques you use in dealing with analysing the triple delta well, when you have like three of these wells. Now I've just drawn a single line because as you like here's your potential well, right? It's width A or 2A, and here's your V naught, right? Well, I can put this in the camera, right? So there's your V naught. But as your A goes to 0, those the two barriers sort of merge in a sense. That becomes so effectively just a single line. And if this depth is your V naught, right? Here's your x-axis as usual. Now you have three delta wells, three potential wells, right? Three of them. Represented just a single line because they're now delta wells, right? And you separate them uniformly, so this distance and this distance are the same, and that distance is b, just little b. Okay, so you have these three delta wells separated by distance b. So we now have four regions. So regions of x. So call this region, starting here going that way to minus infinity, call that region -2, for obvious reasons. And this region between 0 and minus b, call it region -1. And this region between 0 and b, call that region +1, which is 1. And region 2 would just be from when x is b to infinity. Right? So you've got these four regions. And we will solve, well in fact, we don't, again, due to the parity type argument, we can save ourselves half the work. We don't need to solve what's going on here. Because of that parity theorem, you see your V, your potential here is mirror symmetric, right? Therefore the wave function, your U, will have even or odd parity. So we only need to solve this half, and whatever it is, whatever the answer is, we can find the answer in this part. It'll be either odd or even. Your wave function U for regions 1 and 2 will be either even or odd. Right? So whatever it is in here, we can find the corresponding solution, what U is, in regions -1 and -2, right? By symmetry. Great work, Saber. All right. Now I've talked a little bit about in Appendix A. So we can apply these kinds of techniques that we're about to develop for three delta wells. We can extend that analysis to an infinite number. Okay. So think of this the triple delta well now as a stepping stone towards an infinite delta well, or just an array. And you can go to 3 dimensions as well, but we won't do that, and not done in the textbook either. But you can imagine quite readily that this kind of approach could be used in 3 dimensions as well. Have a 3-dimensional array, so a block of material. And therefore you can analyze the behavior of electrons in a crystal lattice. A lattice just being lots of points in a like a 3-dimensional matrix, if you see what I mean. So a lattice. Okay. Now, I'll just state it here that for the case of a triple, 3 delta whirls, you can have up to 3 bound states, wave functions that a wave function that exists over these 3 delta whirls, influenced by the presence of all 3, and you'll have up to 3 different kinds of states, 3 different solutions. Now, if your B becomes large, then your U will decay away to 0. So effectively, then, if B is large enough, you'll just have 3 independent delta whirls. So they'll be acting independently. But if B is fairly small, so the decay, for example, in region 1, so its U, it's decaying exponentially, right? But if it has not decayed to 0 before it reaches this right-hand delta whirl, that the presence of that delta whirl will influence things. Okay, so yeah, we'll do the math soon. Okay, all right. Now it turns out that of these 3 possible maximum bound states, solutions, wave functions, two end up. It ends up. I'm throwing this at you, give you a taste of what's coming. 2 are even and 1's odd, right? All right. Now I ran out of board. I'm already, well, have a look. I mean, I'm putting up like four columns of stuff now, and this is just, I really have to get a bigger board, I think. I just don't have enough stuff. When I get into higher grad level stuff, the number of equations just it'll drown this little board, and I'm going to have to be like a big classroom sized board, I think. Make it a meter longer, or another 10 centimeters taller, or whatever. Okay, well now let's do the nitty gritty. Okay, so now we don't have to worry about what's going on in regions -1 and -2 for reasons of symmetry, right? The parity argument. So that's very nice. So let's concentrate just on regions 1 and 2. Now in region 1, what's going on? Well, your